All right, now I want to move on a little bit. I'm going to come back to this, and I'm going to start. There really is no more math the rest of this section, but I want to talk to you about some really cool stuff because I did a little bit of research in this in grad school, and so it's kind of a subject that I kind of find fascinating, but it's also something that's in your physics books as well. So I'm teaching you stuff that's in your book. It's interesting to me for lots of reasons. So we have talked at great length what happens if you have a magnetic field uniform. Let me draw a couple magnetic field lines like this. So this is a magnetic field. We've talked at great length what happens if, so the field's going that way, if I shoot an electron in perpendicular to this field, what's going to happen is it's going to go whoop, and it's going to start orbiting like this. And if you leave it alone forever, it's going to orbit forever, more or less, okay? But what happens if I don't actually shoot it in exactly perpendicular to the field? That's kind of what I was alluding to a minute ago. I'm going to circle back and talk about that in a minute. What happens if I give it some velocity? Think about vectors. If I give it some velocity this direction, perpendicular, but I give it some velocity this way, parallel to the magnetic field. In other words, instead of shooting it like this, what if I shoot it in at an angle like this? So some of the velocity is obviously pointing this way. Some of the velocity is obviously pointing this way. What's going to exactly happen? Well, I'll give you the punchline. What's going to happen is you're still going to get orbiting, but the particle is going to orbit, and as it orbits, it's going to travel down the magnetic field lines. All right? Think about that for a second. Make sure you understand that. Everything that we've talked about before is exactly true. There is an orbit. It does go in a circle. There is a radius of this orbit that you can calculate from this. There is a period of that orbit that you can calculate from this. There's a frequency and all the stuff that you can calculate because it is truly orbiting the field lines. But if I push it and give it any velocity in the direction of the magnetic field, think about that. We already talked about that. Because it's QV cross B, right? If you have a magnetic field line this way, and if I shoot an electron directly parallel to the field, there is no magnetic force. Because V cross B, if they're in the same direction, there's no angle between them. Sine of 0 is 0. So there's no magnetic force. If I have a field like this, and I shoot an electron directly down the field, absolutely no force is going to be pushing on that thing because QV cross B is 0. So thinking about components of vectors, if I shoot it at an angle, if this is the magnetic field and I shoot this electron in at an angle, some of the velocity of this guy is perpendicular. That's going to lead to an orbiting motion. Some of the velocity is parallel. That's just going to be allowing the particle to move that direction. So what you're going to get in the end result is a spiral. You're going to get like a helix thing, where if you could kind of look at it, it's going to look like a corkscrew. It's going to orbit, but it's going to slide across the it's just going to freely move this direction because there's no magnetic force that's preventing it from doing so. So when I used to give tours of the lab I worked at, the analogy I would give you is when you have a magnetic field and when you have particles that are kind of orbiting in the magnetic field lines, you can kind of visualize them as like beads on a string. Like imagine the magnetic field being a string that's kind of suspended, and imagine the electrons being a bead that's on the string. You know, the string goes right through the bead. So the bead is somewhat bound to the string because it's going right through the thing. But you can slide these beads up and down, no problem, with really no resistance, right? Forget about friction. So I can shoot them super, super fast this direction. They're going to go through, no problem, but they're still going to be bound to that magnetic field line. That's what's happening here. There's a force binding it to the field. That's the center-seeking force we were drawing on the board, but the direction of motion along the field is not impeded at all because QV cross B for that component is 0. There's no force stopping it. So if I had a uniform field like this particle would just move along in a helix, and if I gave it more energy in this direction, the helix would stretch out because it would be zooming along really fast this direction. It would still be orbiting, right? So in physics, a lot of times, when you talk about magnetic fields, you sometimes talk about V perpendicular and V parallel. The perpendicular velocity is the velocity that is going perpendicular to the magnetic field. The parallel velocity is how many meters per second it's just sliding down the magnetic field lines. And I guess the punchline is, when you're talking about, for instance, calculating the radius here, and you have to put a velocity in there, just be careful. If the velocity that you're talking about is coming in at an angle, you don't care about that. The only thing you care about as far as this orbiting motion is v perpendicular. You only care about the motion perpendicular to the magnetic field line, because that's the only motion perpendicular to the field that's going to give rise to this force that's going to actually cause it to orbit. So if you're calculating a radius like this, make sure you're using the velocity that is perpendicular to the field. This velocity is just literally going to be how fast the particle is going to move from A to B, like that. All right. One final thing I want to talk about, maybe two final things I want to talk about that I just find really cool. Let me give you an application from real life. You might say an application from Star Trek, right? But actually, we're doing research in this stuff right now. What if instead of a magnetic field like this, let me get myself a clean board. What if instead of a magnetic field straight like that, what if I constructed a magnetic field that looks like this? It goes up, and then it goes down, like this, and it goes up, and then it goes down like this. Maybe this one kind of goes like this one, maybe like this one, maybe like this. This is called a magnetic bottle, actually. And this is real. This is not science fiction. This is something you can easily create. All you have to do to make a magnetic bottle is get a circular donut magnet right here and a circular donut magnet right here. The magnetic field is going to be really, really strong inside of these magnets. And of course, the lines are going to join here, and it's going to be weaker between the magnets. If I have two magnets here, it's going to be weaker here. But this is a circular thing here. So this is a stronger field here. And this is a stronger field here, and because the lines are farther apart, this is a weaker field in the middle. So this is a magnetic field B, and it's called a bottle. This has lots of uses, actually. They're doing research with magnetic bottles to create nuclear fusion. You'll see why in a second. And they're also using this to build advanced rocket thrusters for deep space, for plasma rocket thrusters. That's why it kind of sounds like Star Trek, plasma thrusters. We actually have plasma thrusters. That's not really science fiction anymore. So this is what we use it for. Let me show you what we have. All right, now let me pretend for a second. Let me just put a particle here. Let me say I shoot a particle in like this. All right? At that particular moment, the velocity, the perpendicular velocity, is perpendicular to the field, let's say. And let's say as a result of that, the force that I'm getting is pushing this guy down. So this is going to be FB. So this situation is really exactly what I've drawn here. I mean, you've got a magnetic field. The orientation is different, but I've got a magnetic field. I've got a velocity perpendicular to it. I've got a center-seeking force that's causing it to orbit. So what I've got here is I've got a force that's perpendicular to, because the velocity of the particle is into the board, it's perpendicular to the velocity, it's perpendicular to the field. So that's right there. Now, if I go over here to the edge, if I thump this guy and it slides down the magnetic field line and gets over here, let's look at what's happening right here. Let me draw with a red color what I've got right here. And without getting into too much detail, the force is not going to be acting straight down anymore. The force is going to be kind of at an angle like this, because the force must be perpendicular to the field. Notice the field is slanted right here, right? And the velocity, the perpendicular velocity, is still into the board. So this force must be perpendicular to the field, which is now slanted, and also perpendicular to V, which is into the board. So that means that the force basically is going to act this direction instead of straight up and down. So you can kind of think of this force, and I'm drawing the force in one position, okay? You've got to imagine this particle is rotating, so the direction of this force is changing the whole time, just like it was changing in the first drawings, but I've got to draw it somewhere in some snapshot of time, so I'm drawing it at this moment. Now, if we take the other extreme and we come over here, then what we're going to have, let me kind of erase that line for a second, then what we're going to have here, this is the particle, and again, notice the magnetic field is kind of slanted right here, so this guy has got to be perpendicular to that, so it's going to go in like this, FB. All right, so I guess what I'm trying to say is these guys are orbiting the magnetic field lines just like this. They're free to move along the magnetic field, but they must orbit the magnetic field. But once they move along, like let's say you give it some energy in this direction, once they move along this direction, the force is now not pointed directly kind of down and it's not letting it orbit this way, the force is slightly cocked this direction. And so as the particle gets over here, the force is not straight up and down as it orbits, it's slightly cocked this direction. So if we take this guy and kind of blow it up, let me actually change to blue. If I take this guy and blow it up, what I'm going to have, let me try to make it a little bit bigger. Then what we're going to have here, this is the force, right? FB, perpendicular to this magnetic field right there. This is a force. That means you can decompose it into two different directions. So you have this guy and you have this guy. So you have Fy and Fx. Let me do it for this side and then I'll give you the punchline. Let's say we have this guy. Let me blow up this over here. So this guy is going this direction. And so this force is acting this direction. So I can decompose this guy into two. Let me go ahead and make it match. I can decompose this into this. So this is Fx, Fy. All right, why am I doing this? What I'm trying to basically tell you guys here is that if you're in a magnetic bottle where the field is not uniform, see, this is not a uniform field. In all of the other examples, I told you, hey, the field is everywhere the same. This is not true here. The field is stronger at the ends than it is in the middle. And so right here in the middle, yeah, everything's orbiting normally, but as he slides toward the edge, he bends over and this force begins to push him back into the center. This force can be decomposed this direction and this direction. Fx is kicking this particle back into the center. So then he's going to go into the center, he'll slide through the middle and he'll get over here. When he gets over here, again, because the field is bent, the force that I'm decomposing here for you is going to try to kick him back to the center. So what you've done is you've literally created a bottle where you've kind of trapped these particles. They can't really get out very easily. If it was a situation like this, the field is totally uniform, the particle can just go on out and, if this was empty space, it would just slide on out there and be gone. But because I have tapered the ends of the field, basically I've bent this force around to kind of try to keep the particles in the middle. And if you make this magnetic field strong enough, the particles will not be able to escape. So that's one way that they try to do fusion reactors. You really want to take a lot of charged particles and try to really cram them together and get them to fuse together. So you create incredibly strong magnetic fields on the end, inject a bunch of particles, they're all going to orbit the field lines and they're going to bounce. They're going to go boom, 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 because when they get to this end, oh, now this force kicks them back. Oh, now this force kicks them back, kicks them back, kicks them back, kicks them back. It's like tennis. And so they collide. They start hitting each other. And hopefully you get some kind of nuclear fusion. And we're not there yet, but that's one way that they're trying to do it. And the other thing you can do is if you build a spacecraft with this, then you can, if you made this end adjustable, kind of like a nozzle, right? Then you can have them bounce, 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 but then you can let them leak out one end. And there's your rocket propulsion. So you can get them to go super, super, super fast in here, and you can kind of open this up a little bit, and then phew, they go out the other end, and so create thrust. That's what you want to do when you build a rocket. You want it to fly out the end. It's super high velocity. That's what a plasma thruster is, one kind of a plasma thruster. So, bottom line is, when you have a strong field, weak field, strong field, you can kind of trap these particles. Now, there's one thing I'm going to say before we close this section off is this is exactly how the auroras work around Earth. Because Earth is a big giant sphere, right? I'm going to put E for Earth. Now, there's a magnetic field around Earth, obviously, so we have magnetic field lines like this. I'll do my best to draw like this. Here's like this guy, a little bit bigger, a little bit bigger. So when you look at a picture like this, the magnetic field is much stronger at the poles of the Earth because the field lines are concentrated there. This is where it's stronger. The field is weaker out here, right here. So if you kind of look sideways, you can kind of see, well, this kind of looks like a magnetic bottle. Strong field, weak field, strong field. Strong field, weak field, strong field. Just like we have up here. Strong field, weak field, strong field. So what you have is particles. You have the sun over here, right? The sun is a nuclear furnace, right? That's all it does is fuse particles and it spews them out into space. It's like it's exhaust, right? And those particles that come from the sun are ions. They're either heavy ions or they're electrons or protons, but they all have charge. A lot of them have charge. So this solar wind is coming towards Earth all the time. And it hits Earth, and as soon as it interacts with the Earth's magnetic field, those particles from the sun get trapped. So when these particles come in from the sun, they get trapped by Earth's magnetic field, and they're going to basically start orbiting the field lines, but they're going to come in at all weird angles, so they're obviously going to have both velocity components, and so they're going to end up doing the spiral business. So they're going to spiral in, and when they get to the pole, that force, because the field is stronger, is going to kick them right back out, and then they're going to go back to the South Pole. And then that force that gets there with the stronger field, like we had above, is going to kick them back out. So you see these particles, they're going to bounce like a tennis match back for all the way. It's amazing when you think about it. All the way from the North Pole, all the way in deep space, back to the South Pole, all the way back, all the way back. How does this create an aurora? Well, our planet is covered in gas, right? It's covered in atmosphere, oxygen and nitrogen mostly. And these solar wind particles, they're coming at super high velocities, bouncing pole to pole. So when you have a bunch of electrons, protons, hitting the upper atmosphere, it's going to ionize the upper atmosphere. It's going to cause the oxygen and the nitrogen in the upper atmosphere to kind of lose their electrons and dance around, and that's going to create light. And that's what we see as the aurora. Same thing going on in a neon tube. When we put electricity in a neon tube, we're basically coaxing all those electrons in the neon atoms to jump around, and when they jump around, they emit light. When electrons in an orbital of an atom jump from one state to another, they emit light. That always happens. So when this electron hits the upper atmosphere of the North Pole, it slams into an oxygen atom and knocks its electron loose, and then that electron comes back down, boom, photon of light comes out. And we see it as these beautiful, shimmering lights in the North and the South Pole. That is because of the solar wind. So if you have really big solar flares that spew out lots and lots and lots of particles all at once, you're going to get a more intense aurora, once it gets trapped in the Earth's magnetic field. Okay, that's a lot of material. We haven't even worked any problems, but there's such a really cool background here that I wanted to make sure you understand how it happens and make sure you understand why it's important. So we talked about the fact that QV cross B, the magnetic force, causes a magnetic field to bend the path of particles traveling in it, as long as they're traveling with some component perpendicular to the magnetic field, and it causes it to bend. Now with our drawings, we've shown you that not only does it bend it, but it actually causes them to go in a circle, and they actually orbit. And you can calculate the radius, the period, the frequency, and the angular frequency of any particle orbiting any magnetic field configuration. And then we also talked a bit about if you give it some velocity that's not just perpendicular to the field, that it can actually orbit but also slide up and down, much like the beads on a string analogy that I gave you. And then same thing here. If we have a stronger, weaker, stronger field, the way these forces play out, basically you're going to get a kickback force. When you get over here, you're going to get a kickback force. It's going to try to push the particle back in. So you can think of two goalies over there. When the ball gets there, they kick it right back in. That's because of the force. It's from the magnetic force that now there is a component of this force that's pushing the particle back into play, so to speak. So you can use that to trap particles for nuclear fusion research, for spacecraft rocket propulsion, and you can also explain how the aurora works, where the particles are bouncing all around. So watch this lesson a few times. We're going to have a couple of sections where we work some real problems and get some real practice with it. It's a fascinating topic, and it's something that actually you can look up in the sky and observe, so I think that's kind of neat as well. Personally, I have not seen the aurora, but I'd love to do it one day. I think it'd be fascinating to see how that interaction really happens. So make sure you understand this material. All of these equations are going to be used quite a bit as we go through the rest of the material there, but you can see that none of them are really complicated, so just make sure you understand where they come from, and we'll get some real practice with them as we work our problems.